Bismillahirrahmanirrahim. In this video, we are going to be talking about the naive Bayesian classifier. The Bayesian classifier and particularly the naive Bayesian classifier are basically based on the theory of probability. So, we will see in the next few slides how they differ from the other classifiers such as the decision tree that we looked at in the last video. So, these type of classifiers are based, in fact all classifiers have some sort of probabilistic value. So, for instance, we can say that training classifiers involve estimating this probability of y given x. Here y is the predicted label and x are the predictors, which can be one or more than one. Basically they are attributes, can be one or can be an entire set having x1, x2 and so on. So, in the decision tree that we looked at, that is an example of a discriminative classifier. In discriminative classifier, and examples include KNN, the decision trees, the perceptron, the neural network, and support vector machines. So, in this we assume some functional form of probability of y given x. So, we are given the attributes and we have to predict the label. And this is done by estimating this value directly from the training data. So, as we saw in the case of decision tree, we made these predictions based on entropy or the standard deviation or any other measure. In contrast to that, the generative classifier, they also predict y given x. However, this prediction is based on calculating probability of x given y. In other words, calculating the probability of observing an attribute given the class. Now, this may seem counterintuitive. Let me give you an example. Suppose there are 20 students in this class and there are 12 boys and 8 girls, and we happen to measure the length of their hairs. So, naturally the length of hair for girls are longer and that of boys are shorter on average. So, if we say average, maybe for instance for the boys it is 3 inches and for the girls maybe it is 15 inches. So, this is just an example. In this case, and suppose there are 20 samples, we have 12 boys and 8 girls. So, when we have the 21st example, and in this case we don't know the gender of the student, however we are given that this person has 7-inch long hairs. So, in the discriminative example, we are going to look at this length and then try to predict whether it's a boy or it's a girl. In the case of the generative classifier, we are going to again look at this 7 inches, but in this case we are saying, okay, let's assume it's a boy. Now, what's the probability that it will be 7 inches given that it is a boy? And then do the same thing. What's the probability that the length of the hair will be 7 inches given that it's a girl? And then we find the maximum probability. So, which probability is it that will maximize this gender to have 7-inch long hair? So, this is the difference between a generative classifier and a discriminative classifier. So, like the previous video, I would like to take it through an example. So, in this example we have several insects, we have grasshoppers and katydids. So, we are measuring the length of the antenna and the length of the abdomen, and this graph gives a very good classification. So we have one cluster or one group over here and another group over here. So if we have enough data, we can plot this graph, and based on this graph we can also plot a histogram. So we can see that there are a few katydids that have very long antennas and very long abdomen size. So this example, for instance, this one, and in this case there are a lot of them that have shorter antennas and a shorter abdomen size. So here we see that it's usually in this range and also in this range. So based on this we can have two histograms, and from these histograms we can convert it. So these are the two histograms. We can convert it into a distribution. This is an example of a normal distribution. So the average is going to be somewhere around here. So this will be x bar for this, and this will be x bar for this. So let's call this x1 and x2, the two distributions. So now if we have a new insect whose antenna length is 3, so we plot 3 here and we measure. So in case of grasshopper, the value here is 2, and in case of katydid the value here is 10. So based on this we have two values, 2 and 10. So naturally the probability of this one is higher. So if we were to classify this, we would assume it to be this category rather than this category. So this won't be classified, but this will be assumed. And in the case the length of the antenna is 7, so we can see in this case it is the reverse. So here we have 3 and here we have 9. So again we will classify this to be the most probable value and not this one. So this is how the generative classifiers work, and mathematically we denote it as D. So D is the attribute that we are looking at. So the observed length here is 7. So in our case D here is equal to 7. So what's the probability C of J? So there are two probabilities, the red one and the blue one. So what's the probability of red given that D is 7, and what's the probability of blue given that D is 7? So this value here is 9 for red and 3 for blue. So with this example we come to what is called the naive Bayesian classifier. It's based on the probabilities that we just saw. So formally representing it, we have the Bayes theorem or the naive Bayesian classifier as this. So as you can see, this is exactly what we are trying to predict, probability of Cj given D. So this is known as the posterior probability. Posterior because we are assuming the category after observing the data. So we say that the posterior probability is made up of the prior probability. So what's the probability of observing this class irrespective of the data? What's the likelihood that if we had observed this class we would have found this data? So this is basically that part where I said that assume it's a boy, and what's the probability that the hair length will be 7, and then assume it's a girl, and then what's the probability that the hair length will be 7. So this is that part, the likelihood probability. And then this is the evidence, what's the probability of observing a hair length of 7 irrespective of the gender. So the posterior probability, and here they are listed what each of them means. So probability Cj given D is the probability that D being in class Cj, and this is what we are trying to predict because we know the data and we are trying to predict the class. Probability Cj is the independent probability of observing the class in the data. So this is irrespective of the attribute D. And probability of D given Cj, this is the likelihood and is the probability of observing the value D in the class. So we are going, in this case we are assuming the class and then finding out what the probability of observing this data. And this evidence, as we will see in the example, is usually ignored. So it is there in the formula, but in practice we usually ignore it. And when we see the example, we will see why we do that. So a few of these slides have been taken from the University of California at Riverside, and this is one of those slides. So I've given the reference in the title in the first page of the slide. You can see that for if you like the details. So this is a very good example, and it's trying to predict a person. So assume that we have two classes, C1 is male and C2 is a female. We have a person whose sex we do not know. Let's call that person Drew or D. So Drew, as you can see, it's a name, and it's a name that occurs in both genders. So we're trying to predict just by knowing that name whether that person is a male or a female. So what's the probability? We have that naive Bayesian formula. So I've written it over here, and instead of using D and C, since we know the values, so what's the probability of male given Drew? This is the posterior probability. So this is going to be the so if you can look from here, this is going to be the likelihood, the prior, and the evidence. So this is the likelihood, this is the prior, and this is the evidence. So what's the probability of male given Drew is the same as assume it's a male. What's the probability? The name is Drew. What's the probability of males in general, and what's the probability of Drew independent of the gender? As we said before, we tend to ignore this part, and the reason being that because it's the same for male and female. So if you're comparing two fractions and they both have the same denominator, you can ignore them and then just look at the numerator part of it. So suppose this is the data that we have. Now we have to find this officer. So officer Drew, whether it's a male or a female. So we have our formula. What's probability? So let's calculate this probability. Probability of D given male. So once we say given male, we are only going to look at the male sample size. So this is one value, this is the other value, and this is the third value. So there are three values. What's the probability? It's Drew. So it is 1. There's only one person among the male. So this has a this person has a different name, and this person has a different name. So this here is 1 by 3. There are 3 males total, and only one of them is called Drew. So let me write it here. So this is going to be 1 by 3. So multiplied by how many males do we have? We have 3 males and 1, 2, 3, 4, 5 females. So this is going to be 3 by 8. So 3 males out of a total of 8 data points, and divided by probability of D. So what is the probability of D? D is Drew, 1, 2, and 3. So now we are ignoring the gender. We're just counting the number of times this name occur. So 1, 2, 3. So this is going to be 3 by 8. So this if I ignore this part, this is going to be 0.125 and divide by 3 by 8, and same with this, and this will be 2 by 5 because there are 2 this and this, and multiplied by this is going to be 5 by 8 and divided by, so you can see this and this are the same, so we have 3 by 8. So in this case the value is 0.25 divided by 3 by 8. So as we see that this fraction and this fraction are the same, so we can ignore it and we can just compare these two values. So we will have to find the max value in this. So as we can see that this 0.25 is higher, so therefore this person is a female. So here is the calculation, And using this very simple example, we can see that how the naive Bayesian classifier is able to predict the class of the data, of the unobserved data. However, this was done for only one attribute. So D, or the name, was only a single attribute. What if we have a data in which there are more than one attributes? How do we deal with that scenario? So to understand that, we have to look at how probability works. So here's the basics of probability. I'm sure most of you know this, but just to refresh. So suppose we have two 6-sided dice, they are rolled simultaneously, and we have the following scenario. So A is an event such that the first die lands on 3. B is an event that the second dice lands on the side 1, and C is that the sum of the two dice equal to 8. So to answer the following questions, the first one is, what's the probability of A? So what's the probability that the first die will have 3? It means that, so if I label this one as 1 and this one as 2, so I'm not bothered what will happen with this part. I'm just saying what's the probability that this is going to land with 3 on the facing upwards. So there are 6 sides, one of them is 3, so the probability is going to be 1 divided by 6. So this is the probability of P of A. And similarly, what's the probability of P of B? This is also 1 by 6. And what's the probability of P of C? Now this is an event that takes both dice into consideration. So for the sum of the two dice to be 8, I have the following scenarios. I can have either 6, 2, so the first die shows a 6 and the second die shows a 2, or I can have 5, 3, and then I can have 4, 4, then I can have 3, 5, and finally I can have 2 and 6. So, here we go, eraser, and let's erase this part. And so this is 2 and 6. So 1, 2, 3, 4, 5. So in total there are 36 combinations. So the first dice can have one of the 6 values, and the second dice can also have one of 6 values. So total there can be 36 possible combinations. Out of those 36, 5 of them will result in the sum being equal to 8. So in this case I have 5 by 36. Now let's go to a slightly more trickier part. So what's the probability that of observing A given B? So what's the probability of observing that dice 1 lands on 3 given that dice 2 has already landed with a 1? So since this is A is independent of B, it doesn't matter what B is, the probability of landing of side 3 is still 1 by 6. So this is the same as 1 by 6. Why? Because A and B were independent events. However, if I look at this probability, what's the probability of having C given that A has occurred? So if A has occurred, it means the first die has a 3. Now what's the probability that the sum will be 8? The only way the sum will be 8 if the first die is 3 is having this one. So there's only one possibility here, and so the possibility is 3, 5, and the total probability here will be 1 by 6. Now notice that we are not using 1 by 36 because A is already given, so we know that A has occurred. So A is no longer 1 by 6, that the probability it will have a 3. No, we are given that A has already occurred, so A is already a certainty. So the probability that A have occurred has now changed from 1 by 6 to 1, because now we are given that as a certainty. So what's the probability of C given A? This is observing this scenario, and that's 1 by 6. Now what's the probability of A and B both occurring. Since these are independent events, so probability of A occurring is 1 by 6. The probability of B occurring is also 1 by 6, and since they are independent of each other, we can simply multiply them and get 1 over 36. And finally, what's the probability of A and C occurring together? And that probability will be probability of A. So what's the probability of A and C occurring together? This is the same as probability of observing A and probability of observing C, given that A has already occurred. So this is going to be 1 by 6 multiplied by 1 by 6, and which is 1 by 36. So probability of A and C occurring. So probability of A occurring is 1 by 6, and probability of C occurring when A has occurred, it's going to be again 1 by 6. So basically we are talking about this scenario again. So this is 1 by 36. Now, is probability of A and C the same as probability of A and probability of C? And the answer is no, they are not. Why? Because C and A are not independent events. If A has occurred, then there's only one way C can occur. Otherwise, there are 5 ways in which C can occur. But if we must include A, then there's only one way in which C can occur, and that is this way. So to answer this, it is no, the probabilities are not the same. So with this refresher about basic probability, let's move on to how the naive Bayesian classifier works. So in a sense, if as you remember, I said that the attribute x that we have can take multiple values x1, x2 and so on up to xp. So these are different attributes, and in the naive Bayesian case, so we have I've just summarized all these things here. So in the naive Bayesian case, when we have multiple attributes x1, x2 and xn, what is naive in fact, if you have asked the question, why do we call it naive Bayesian, what is naive about it? So naive Bayesian approach, the part that is naive about it is that it assumes all these attributes are independent of each other. So if you're assuming they are independent of each other, similar to this case A and B, you can simply multiply these attributes. So that's what we are going to do here. So we're going to multiply these attributes. So x1 given C and x2 given C and so on xn given C. We are simply going to multiply all the attributes calculated independently. So how do we do that? Let's look at another example, and this is an example that we have seen before. So this is our data. We have outlook, temperature, humidity and wind, and we have to predict whether we're going to play tennis or not. So the first thing to do is to fill this probability tables, because we have to compute the probabilities given yes and given no. So let's fill these probability tables. In this case, we are trying to predict that the probabilities of the attribute outlook. So we have the 3 possible values for outlook. We have sunny, overcast and rain. So we have listed them over here, and then the categories can be yes and no, so they occur over here. And now we are just going to plug in all the probabilities. So what's the probability that it's going to be sunny if the output or the category is yes? So for the sake of simplicity, all the yes here are coded as red. So all we have to do is figure out 1, 2, 3, 4, 5, 6, 7, 8 and 9. So there are total of 9 yes samples here, and since it is 14, it means the no's are 5. So yes is equal to 9 and no is equal to 5. So coming back here, so outlook, what's the probability? It's going to be sunny given that it is yes. So we'll just have to look in all the yeses and find how many sunny do we have. So this is not sunny, this is not sunny, not sunny. We have one over here and then we have another over here. So this probability is going to be 2 by 9. So overcast 1, 2, 3, 4. This is going to be 4 by 9, and rain we have 1, 2 and 3, and this is going to be 3 by 9. A good way of seeing whether you are doing this right or wrong is that outlook can either be sunny, overcast or rain. So you can be 2 plus 4 is 6 plus 3 is 9. So this has to be equal. So 9 by 9. You know that you have calculated these probabilities correctly. You didn't miss anything. Same you can go with the no. So again, how many sunny do we have? 1, 2, 3. So this is going to be 3 by 5. And then how many overcast do we have? It is none. So we have 0 by 5 and just 2 for rain. So we have 2 by 5. Again, this is going to be 3 plus 0 plus 2 by 5, which is 5 by 5. So this is correct. And in a similar manner, we can fill such a table for temperature, humidity and wind. So these are the tables for outlook, humidity, temperature and wind, and this is the probability of whether it's a yes 9 by 14 or it's a no 5 by 14, and these are irrespective of the values observed for the 4 attributes. So using this data, we can now predict a new data. So let's assume that the new data is this X. So we are given outlook equal to sunny, temperature equal to cool, humidity equal to high and wind equal to strong, and we are asked whether we are going to play tennis or not. So what we can do is we can have the maximum probability. So as I said, you are going to calculate, you are going to assume it's a yes, compute these probabilities, then assume it's a no, compute the probabilities again and take the maximum of these two probabilities. So maximum a priori probability. So let's calculate it's a yes. So outlook equal to sunny for yes. We are now assuming it is a yes. So what's the probability that it's going to be sunny? This is so this is going to be 2 by 9 multiplied by what's the probability that the temperature is cool? So this is 3 by 9 multiplied by the probability that the humidity is going to be high. This is again 3 by 9 and multiplied by that probability that the wind is going to be strong, which is again 3 by 9. So multiplied by, since we assume that it is a yes, what's the probability of being yes? That is 9 by 14. So this is going to give me 0.0053. And now we are going to assume that it's a no and then recalculate these probabilities. So what's the probability of sunny in a no? This is 3 by 5 and multiplied by cool given no, says this is 1 by 5 and multiplied by a high a high given no. So this is high given no, this is 4 by 5 and strong given no. So this is going to be strong given no, this one, and it's going to be 3 by 5 multiplied by, since we assume it's a no, multiplied by the probability of no, which is 5 by 14, and if you calculate that, you will get 0.0206. So now we have to apply the maximum a priori rule, which simply means that looking at these two probabilities and using the max value. So if you use the max value, this is 0.0206. so this means that given this data, play tennis equal to no, since this is for no. So the prediction here using this algorithm is that play tennis is going to be no. We're not going to play tennis on the day when it's sunny and the temperature is cool and the humidity is high and the winds are strong. So this is for the case of multiple attributes. So you can see that it's a fairly easy algorithm. All you need to do is to fill these tables, and there is a very low chance of making a mistake, since as you're filling the table you can simply see that 2 plus 4 is 6 and 6 plus 3 is 9, so is the same. Then 3 plus 2 is 5, so this matches as well. So 2 plus 4 6 and 3 9 again, and 2 plus 2 plus 1 is 5. So you can verify while you are calculating these probabilities. So in summary, the naive Bayesian classifier is based on the independence assumption between the different attributes. So training is very easy and it's very fast, and testing is straightforward because it just involves looking up the tables and multiplying the probabilities together. So there is nothing complicated in terms of computational complexity. You don't have any loops there, you don't have any ordering, any sorting or anything of that sort. And it's a popular generative model, and its performance is in many cases very similar to other state-of-the-art classifiers, and it has been used in many successful applications. It's a good candidate for Bayes learner in ensemble learning. Ensemble learning is using multiple learners to reinforce what we have learned and increase the accuracy of that. And apart from classification, it can do a lot more. For instance, it's used in news classification, it's used in email spam filtering, it's used in facial recognition, it's used in sentiment analysis, in medical diagnosis, in digital handwriting recognition, weather predictions, and many other application areas. And the basic or the probability used here is also applied in other algorithms and other application areas as well. So I hope this topic and how to use the naive Bayesian classifier is clear. If you have any questions, you can either ask in the comments below, or you can email me, you can ask us on the class MS team, or you can ask during the interactive session later in the week. So that's it for today. Thank you.